The Otto DIY open source project is an amazing activity for people to learn about building robotic devices in a simple and low-cost manner. There are many different devices, all based on the Arduino Nano hardware and its peripherals, all of which you can obtain pretty cheaply from a number of different sources. If you have your own 3D printer, you can not only print out Otto's body, but you can customize it in almost any way you want. This video is attempting to explain and answer some of those issues that users have with providing adequate power for their robot. Your robot may be restarting, you may have some other issues, maybe you've damaged your Nano. I'll discuss some of the power options, but I'm going to focus specifically on versions of Otto that use the Arduino Nano V3 design and its clone design. So we'll take a look at that. This is a version of the Arduino Nano clone, a little different than the genuine, basically the same thing. And this is the shield, which was designed not by Arduino, but is used in most of the Otto designs. Now these can be gotten, I think these prices here for AliExpress, I think I got 2 nanos and 2 shields for under $10, and that was taxes in and shipping. An actual or real Arduino Nano V3, pretty well the same hardware. It has a little bit different driver for the USB, but here in Canada, $34 plus shipping plus handling. You could easily pay $60 for one. So unfortunately, buying them offshore is often cheaper, but we're going to look at specifically this hardware when you're building your Nano. Now, you may have come across an article called 10 Ways to Power Your Robot. It was actually based on an earlier article here, or I think it was anyway, certainly got a lot of the same information, which was based on the Arduino Uno. So you may find some of the information in here is not really applicable to the V3 design. We'll talk about that as we go along. So as I was building my basic Otto, and I haven't fully built it, I went to choose a power system for it, and I found quite a few different suggestions. I also read many reports of Otto reset starting, some people frying regulators, so I decided to provide some information on why that might happen. We're first going to look at some of the servos, because they tend to cause some of the issues. So we'll look at the servos which are typically used. This is a Tower Pro plastic server, an SG90. It's in the basic design, and the SG means it has plastic gears. This is how much 1.3 kilogram per centimeter is how much torque it has, or how much it can lift at distance. And you'll see inside it's made of plastic gears, and these can strip a little bit, so it has if you try to force it too much, you may damage the gears inside here. Any motor, whether it's a servo or a motor running wheels on a robotic car, it can draw a lot of current, what's called startup current or stall current. If the motor doesn't start, it's going to require huge amounts of current to try to start. Once it's running, you'll find that this will go way down to about 6 to 10 milliamps. But the startup current or stall current, or if your servo gets stuck, can draw up to almost an amp of current. So you should be aware of that when you're looking at power supplies. As an upgrade, you can use a metal geared servo. All the gears inside are metal. They're a little stronger, they won't slip as much, weighs a little bit more, has a little bit more current to draw when it stalls or if it gets bound up a little bit. Called an MG90S. There is an MG90D out, which is an upgrade even of this. On some larger models based on Otto, I have seen the S3003 servo. Now this is quite a bit bigger servo, weighs 37 grams, but this can draw up to 2 amps. So those are some considerations you need to be aware of when you're designing what power supply or how large your batteries need to be to power your Otto. Now, all motors are noisy. They're not really electronic friendly. And here's a couple that of oscilloscope traces. This is a signal which is turning a servo off and on with the servo actually not being powered. So this is what the signal would look like going into sort of a dead servo. When the servo's on and responding, this is how much noise you can have here. So sometimes this noise can cause problems, and we'll take a look at how you might solve that. So how much current or capacity, how much power do we need to really run an Otto? Well, I did a very simple test of my half-built Otto with 4 servos, and we'll take a look at that. We have a gauge which goes from 0 to 1 amp, and you'll see the little indicator in here. This will move up and down. This is going to measure, it's going to record the maximum peak current. So we can look at what it might require here. So we'll take a look at our... So what I have here is a half-built Otto. It's got 4 servos in it. I'm powering it up from a bench supply that can supply 3 amps at 5 volts, so I've got all the current I need. So you'll notice this bar down here is going to give me my current. You can see that's 300 to 400 milliamps pretty well constantly. And you'll see that running 3 servos here peaks at almost half an amp. And as I say, I'm only running 3 out of the 4 servos continuously, 1 staying still. Now we're going to look at what happens if Otto runs into a little resistance on its servos. And again, take a look at this bar graph underneath here, and you should see it go up to 800 or 900 milliamps. Now I'm not stopping a servo, I'm just giving it a little resistance. And you'll see the peak easily goes up to 700-800 milliamps. So that was a little test of probably the simplest Otto you can build with the plastic gears. Now let's talk a little bit about heat. How much heat can components dissipate before they actually get damaged? And we'll go into talk about power supplies and powering your Otto right after that. There's a bunch of resistors, and what you'll see here is that this is likely about a 1/4 watt resistor. If you want to dissipate more power, you have to get a bigger package, or else the heat will damage this component. This is probably a 1/2 watt. I don't think it's probably a 1 watt resistor. 5 watts is a bigger package, and here we go up to 10 watts and larger. So these are fairly large packages. Now, on your nano board, you have regulators dissipating heat, which are pretty tiny. Any component that's dissipating heat in an electronic circuit, you only want to dissipate about 1/4 to 1/2 watt unless you are adding some metal to it to heat sink it and taking some additional cooling, having fans or whatever. So let's keep this in mind as we discuss further slides here. How do we compute power in a circuit if we know the voltage across the component and the current going through it? And this could be a resistor, but it could be a voltage regulator. Just basically can be any component in here. So let's suppose we've got a voltage regulator, and we've got 9 volts here, and maybe we've got 4 volts here. And maybe through our regulator we're getting 1 amp of current. How much power does it dissipate? Well, it's just the change in voltage times the current will give us our power in watts. So here our change in voltage, or our difference in voltage, is 9 minus 4, which is 5 volts times 1 amp, and that's 5 watts. Now that's quite a bit of power. Let's look at what 5 to 10 watt power supplies actually look like in size if they have to dissipate that much power. Here we have a 10 watt this is an audio amplifier, and this cube tap, you probably have one in your home, can generate 5 volts at 3 amps or 15 watts out. And you'll think, well, Why don't we all use these, or why is this smaller than this? Well, there's two different designs in play here. This is using a linear regulator design. This is using a switching regulator design. Well, since this is smaller, why wouldn't we use all switching regulators? Switching regulators use a signal that goes on and off, and it does provide some noise. And if you hold a switching regulator up to different devices, you may hear some noise. People can actually hear some switching regulator noises. If it's really high frequency, if you have a radio that's an AM band, you may hear some static. These types of power supplies are used in audio circuits where they can't tolerate any noise, so we need to use a linear regulator design here. But you can see these are quite inefficient. It's quite large. It can only dissipate 10 watts, and usually on the back here there's some metal that's dissipating or cooling the devices. We've got a bunch of different ways that we can power our Otto. Let's look at all the different inputs and talk about them here. This is the USB input, and typically you'll have a cable which will come from your computer powering this. What you'll find here is that on the Nano itself there's a little, it's called a Schottky diode here, that provides about a 0.3 volt drop, and it supplies basically goes from here to the +5, this same pin right here. And this is supplying power to all these outlets here, or there are pins here that are going to power your servos or peripherals or other devices. So you can power Otto from the USB port. You have something called, they call it a Japan jack here. It's a I think it's a 5.5 millimeter round, typical round jack that you'd see off an adapter. And you can feed 7 to 12 volts in here. We'll talk about why that's going to be 7 volts, but there's actually a silicon diode in here which then goes to the V-in pin. And this V-in also goes to the Nano. And the Nano has a regulator in it. So if we were to feed 12 volts in here, the 12 volts would go to the regulator in the Nano, which is producing +5 volts, and there's a the +5 would connect to the same +5 that I talked about before, and that would power all your devices. So potentially you could put an adapter in here. It would take its signal into the Nano that would produce 5 volts for the Nano itself to power it, and it would power all the devices on your board here. Now, using these little pads here, you can actually wire directly to them. There's 5 volts in ground, and you could actually have a battery pack here that was providing +5 volts, and you could attach it in here. That 5 volts would go to all your pins here. It would actually power your Nano because 5 volts is attached to that, and your Nano would work that way. Or if you want to use V-in similar and you didn't want to use this connector, you can just wire directly into this pad here. Now, there is there's a diode from this V-in to here, which then goes here. Let me make that a little clearer here. And then this V-in goes up here. And you drop almost a volt here. That's why you'll get that this has to be a volt higher than here. You can get away with 6 volts. So those are a bunch of different ways that you can apply a voltage into your Otto. So let's suppose we want to use this Japan jack with V-in and a 9 volt adapter. So on the Nano itself, the V-in from the Japan jack will be routed to the V-in pin of the Nano. And let's just suppose we forget about the diode there. We've got 9 volts feeding in. Our little 3-terminal regulator is going to provide 5 volts out. And we said, and if you watch the video there, you can see we're pretty well getting about 1/2 of an amp consistently being drawn through the servos. So that's how much current is going to go through this device. Well, 9 volts one side, 5 volts the other. We got 4 volts as a difference. We've got 1/2 of an amp going through it, and that little device is going to dissipate 2 watts of power. Now we said before that really all we want to dissipate is about 1/4 to 1/2 a watt. 2 watts is going to damage this. In fact, it's going to cause it to sizzle. And a lot of people have blown up. This is the little regulator. It's on the bottom of the V3 Nano. A lot of those have blown up. Now some people have desoldered them and gotten the parts and put them back in and gotten a working Nano again, but at $2 or $3 you would just order a new one. Now not every Nano uses a linear regulator. This is a linear regulator and they're quite inefficient. The newer Nanos, like the Nano Every, it's got a switching regulator here. So you can, in a switching regulator, it's much more efficient. And you can, I think the spec is, you can draw actually 1.2 amps through that. But if we went back to our design, and one question might be, if I was using a 9-volt adapter, how much current could I provide before I would damage this device? Remember we said maybe only 1/2 a watt. So if we had 5 volts here, we have 4 amps. Well, I could only have 1/8 of an amp that I'm putting through this to keep the dissipation here under 1/2 a watt. Even if I said, well, I might want to stretch it to 1 watt, this would be 1/4 amp. So we couldn't put much current through this. Compared to, and this is why the genuine Nanos changed their design, they went away from a linear regulator. The genuine Nanos in the V3 had a linear regulator, but they switched to a switching regulator and they could supply 1.2 amps without this type of problem, and that's just because they went to a switching regulator design. Well, we talked about feeding V in with different places. We could attach a power supply with some batteries right to V in right on the board. Would there be any issues with this? Well, if we use the jack, we need at least 7 volts, and you're not going to typically get 7 volts if you're using, say, AA batteries of really any type. They'll give you 6 volts, but not 7. Nickel metal hydride have an AA form factor, but their cell are only 1.2 volts, so you're even getting a lower voltage there. You're only getting 5 volts. You could, instead of putting the batteries and tying them to V in, you could tie them to the +5 right on the side of the board. The problem, if you're using alkaline batteries, they probably won't give you anywhere near an amp of discharge current. So even though you'll get maybe 6 volts, it is close to 5, you can't get an amp of current. Metal hydride can, however, supply. You can get very large or high discharge batteries in this version. I'm not sure how much they would cost, and they can supply up to 2 amps. So this might be an option. However, all batteries drop voltage as they use. Now with the Nano, this is not a problem. Nanos can work, I think, from about 3 to 3.3 probably to 5 volts pretty easily. So as the voltage drops, the Nano will still work. Your servos have a spec of 4.8 to 6 volts, but they'll actually work down to 5 volts. That's not an issue. But you may have some peripherals that will only work at 5 volts. It depends on the design of the peripheral you're using. So this may work for some of the simple Otto designs, but you may have issues if you have peripherals which really require 5 volts. but that's one solution. What about feeding the USB? Well, there are no fuses in the Nano V3, so you're not going to get a fuse that's going to trip. The USB feeds VN through an actual Schottky diode, which I mentioned there. You'll get a little bit of a drop. But the USB will provide, actually the USB connects directly, doesn't feed VN, sorry, this is a mistake. It feeds the plus 5 volts through a diode. So you have the USB, have a Schottky diode, and you have plus 5. So if you have plus 5 volts here, you'll get a little drop of 0.3. You'll probably get 4.7, and that's feeding your Nano, which is fine, and all your servos, which will work fine too. You can usually get about 1 amp through most USB outlets. Be aware that the USB 2 standard, however, only needs to provide half an amp. So you may have a passive hub or some devices that can only supply half an amp, but most can supply up to 1 amp of current. And if you have a diode in here that's only dropping 0.3, 0.3 times 1 means you're only getting 0.3 watts through this diode, so you're not going to damage the diode. Some USB banks can provide 2 or 3 amps. And if you have an Otto with a lot of servers and a lot of hardware on it and it's drawing a lot of current, you could power it through here, but I'd be a little worried about that diode, because if you have 2 amps, you're now starting to get 0.6 watts or more, and that diode will get hot and you could damage it. Plus, you're not typically going to have a large power bank on top of your Otto and plugged into this if you want Otto to be fairly portable. These are some of the schematics of what you'll find in the V3 design. This is the USB. You'll see the little Schottky diode here, and this provides plus 5 volts, which connects to 5 volts of the Nano here. What's not shown is a chip for the USB interface. Now the clone has this chip to run its USB interface. A genuine Nano has something different. What does that mean? Well, if you're using the Arduino IDE or the Blockly Otto software, you may have to, or you will have to, if you're using a clone, get a driver for the CH340, and then those two devices, 2 pieces of software will work. On the Nano, this is the regulator. We've seen this design. Comes from the VN pin, and it's just a little linear regulator, nothing fancy, but very inefficient. And so this, both the USB that attaches to the Nano and the VN, those pins were only designed to power the Nano itself. Maybe one small current peripheral, but they're not designed to run a lot of servos. The shield board looks something like this. So you can see the jack here with the diode, and this is this V-in that you can get on the side of the board. It runs into the Nano. There is another regulator here which can provide 3.3 volts on the header. We don't typically use these, and or at least I haven't on my Otto designs. And these are the where you'll plug in your servos here, and you'll see plus 5 and ground. Now, if we want to use batteries, what are sort of our options? Some of the current solutions use lithium-ion batteries because they're very safe. And the common designs are this one, a 16340 and an 18650. And Otto doesn't tend to use this, but there are other designs that we'll talk about which are using this. And you can see the size of these, the relative size of these 2 batteries relative to the size of Otto. So this is not that usable because it's just too large. And you can see the 16340 will fit easier into the current size of Otto. But the larger the battery, the more capacity it will have, and sometimes the more current it will allow you to draw. So sometimes the larger batteries are better if you have a lot of servos. The problem with getting batteries is that it's hard to buy batteries from cheap batteries online, because there's a lot of not very reputable stores out there selling batteries. Here's one example of a GTF company that's selling a battery. This is the 18650, which it says has almost 10,000 milliamp hours. Now, milliamp hours is the capacity. It's not how much it can discharge. But let's just suppose we were drawing 1 amp from it, which is 1,000 milliamps. Well, we would expect this to last for about 10 hours because that's the capacity. 1 milliamp by 10 hours is 10,000 milliamp hours, roughly what that is. But when people actually tested this battery, they drew 1 amp from it. It only lasted 35 minutes. So really this battery gave roughly about 500 milliamp hours. So you may buy something, you're thinking you're getting an amazing battery, but in reality, this is what you're getting. And most people don't realize that because they don't have equipment to measure it. By the time they find out, it's too late. Other problems with using these batteries are there are 2 versions of these types of batteries. In order to protect these batteries from short circuiting, some of them have a printed circuit inside here which protects it from short circuits, and that protective board can be a problem. If Otto all of a sudden a servo gets stuck and it draws a lot of current, the protection board may shut down the battery and Otto will reset. So if you buy batteries, you want to make sure they specifically have large discharges that you need, discharge rate, and that they have no protective board. So you got to be a little careful on what type of batteries that you're using here as well. We're going to look at some other solutions besides Otto and what they've done to power their board. So I came across this design called the Sloth. It's from Sunfounder. And originally, this is what it looked like. They were using 2 of these 18650s, and then each of these cells provides about 3.7 volts. And these were in series, so they were adding together to get about 8.4 volts. And this original design, when it first came out, they were feeding this through this Japan jack. And very quickly, I think they found, because this is fairly heavy, a lot of servos which are very much larger, I think they found a lot of their clients, their little nano was burning out because it was just overheating the little regulator. They were using the V3. So they very quickly designed their own Shield I/O board. And what you'll see, what their board is neat, is that it's now using a switching regulator design. And this switching regulator design, I think it's a 2596S. This is regulated at 3 amps. Now there's no heat sink here, nothing to cool it. So if you were running at 3 amps continuously, you would burn this out. But this can handle easily 2 amps pretty continuously, and if servos got stuck and they drew 2.5 amps for a short period of time, maybe a second, this would be fine. You can generally tell these are switching regulator designs when you see a large inductor here. Now there's another thing which potentially is a really good design here, and I'm not sure if they're doing this, but if we have a cell here that has 8.5 volts and comes in here, we could take that 8.5 volts and we can feed that right here to the VN of our nano board. Now in this design, the plus 5 volt pin of the nano, I wouldn't have that attached to the board. What would happen is this 8.5 volts is also going into this switching regulator design, and that has a 3 amp output, and that would be feeding VCC in all my pins. So you actually get two sort of isolated voltages. One for the shield board and your servos, and one here, this 8.5 would go to the nano. The nano has its own regulator to provide 5 volts, but it would only be providing 5 volts now for itself. So by separating these two voltages, you might get a much more stable operation, because the noise that might be generated on the VCC from the servos doesn't affect the nano. This Sunfounder also had a heavier duty version of this called the Raspberry Pi version, which requires even more power. And what they did here is they used these two 1850s, and on the back of it they had their own power board, which they can charge these two batteries with. If you don't have a charger, typically in the other design you would take these out and you would put it in your little, you'd have to have your own little charger for it. And this provides 5 volt 3 amps right out. That is the switching regulators right on this board. And then this plugs into what's called a Pi hat board. It's their version. It's the Raspberry Pi's version of the Shield. So that's a solution that they have for their larger board. Some have, I've seen one design in the, they've upgraded the Shield to put a little heavier duty regulator here. This is called a TO220 package. However, it sits underneath where your nano goes. Now it can dissipate more power than these little LM1117s, but you're not going to get very good airflow, especially if it's underneath this nano, which is going to act sort of as a little tent for it. Typically in linear regulators you'll see these types of designs where you have a heat sink around it, and that's going to keep this part cool. Without that, these are still going to blow up if you put too much current through them. Oops. This is currently the recommended power pack for Otto, and I've just received this. I haven't tested it yet, but it basically is a really nice little board here that can provide up to 1.3 amps of output current at 5 volts. And it can do that just using a single 3.7 volt cell. So this is the cell that I've purchased, and it's a 16340 package. A single cell, so this is the voltage. So in here is a little boost regulator. This is going to boost that 3.7 up to 5 volts, and we're going to feed that here. Now, in order for this to work, you have to have a high discharge battery, and it's hard to find high discharge batteries. The specification is actually that it can provide 2.5 amps. So it's 700 milliamp hours will tell how long it will last. If you take 1,000 milliamps from it, or 1 amp of current, it's not going to last an hour. It's going to last less than an hour. But it can discharge at once up to 2.5 milliamps. Well, why might we need this? Well, power out in a system has to equal the power in. So if we're running our Otto, and let's suppose we need at least an amp out, then we've got 5 volts at 1 amp, and that's 5 watts. Our input is a 3.7 volt cell. We don't know what current we're going to have to use here, but let's suppose our little regulator is 90% efficient, so we've got 0.9 here. So we need to figure out what value of current do we need that we're going to draw from our battery in order to equal the same power that we're getting out. So what we would do to calculate that is take 5, I'll divide that by 3.7, divide by 0.9, and we'll find that that will be about 2 amps. So because we've got a smaller voltage than we're getting out, we're boosting this, we're getting a higher voltage. We need more current. We need at least 2 amps going into this device in order to get 1 amp out. So even if we had this circuit, if you don't have a really good battery in here that can provide 2 amps at once, you may not get anywhere near 1 amp out. So you buy a cheap battery, maybe it's only giving you half an amp is the maximum capacity. You may find that this circuit just can't provide much more than 200 or 300 milliamps, and your Otto is resetting all the time. And in this case, the reset is because your battery just doesn't have the capacity to deliver current really quickly. So why does Otto reset? Well, Otto resets usually when he's drawing more current than the power that you're providing in can sort of source, whether it's a battery system or what it is. And when that happens, usually the power system shuts off, so Otto shuts off. And then when Otto shuts off, the power system comes back up because there's no load, and Otto restarts. And it just goes through that cycle. So you'll see Otto go through a reset cycle. How can we fix this? Well, don't activate all the servos at once when you're writing your software. I think the Blockly code and the Arduino IDE for Otto tries to slow the servos down. It may even try to sequence the servos so servos aren't on at the same time. But you can do things in software so you're not running all the servos at once. For people that are in some of the other types of servo designs with robots I've seen, a lot of people actually budget basically 1 amp for servo. And if you have 6 servos, they're saying, well, we might need a 6 amp supply. Now that's not realistic on a small portable system like this, but just be aware that many servos running all at the same time are an issue. You might have a servo binding. That is, maybe you've tightened down some parts as you've built Otto, and the servo can't turn the leg freely, so there's a lot of resistance. When that happens, you'll find that there'll be a lot of current that's drawing. Now, you should not turn servos by hand. They can get damaged, especially the plastic ones. But when you're building, just be aware that all those joints can turn very freely as you're connecting your servos up. You can also get too much noise. I had an issue where I had a lot of leads running my servo from the video that you saw, and my Otto was resetting quite often. And long leads, the noise from servos can get induced into long leads, and your what is generally a very nice 5-volt signal can start to get noise and sort of do this type of thing, and when the power supply drops out, may be enough to trigger a reset in Otto. You can sometimes get around this by adding what are called filter capacitors. Really, they're capacitors of this size and this size. The smaller capacitors will get rid of very high frequency noise, and these much larger value capacitors can help to provide a little extra oomph to your power supply to get rid of any sags or drops in your power supply that the servos, the motors might require as they start up. So you would put those capacitors very close to where the servos actually attach into your board. Keep your leads as short as possible. You don't have much control over leads, but don't have any longer leads than you need. If I were building my own power supply for Otto, what would I do? Well, here's, I guess, maybe a solution if I had a lot of servos and a lot of things, and I needed a power supply that I figured that was going to be a good 2 to 3 amp power supply. You can buy LiPo batteries, lithium polymer batteries. The problem with LiPo batteries is they're a little more dangerous. They can catch fire, and so people recommend that they're stored in a fireproof bag. They come in 1S, 2S, and that's a number of cells. You can buy a very simple little 2S, that's 2 cell. Each cell is 3.7 volts, so this little battery is very small, and it actually fits between the servos in Otto's body. And I would attach a 2S LiPo server, and these are very high discharge. This can easily give you 10 amps of current in a very short period of time. I would connect that up to a switching regulator, and these are very small and very cheap. You can buy these for about $2. I think this was about, probably by the time tax is going to be about $15 for this type of battery in Canadian funds. And then I would attach this with a 4-pin connector to these 4 pins here. I would take the 7.4 straight from the battery, and I would attach that into my V-in here of my Nano. I would make sure my Nano plus 5 pin didn't connect to the board. And I would take the output of this regulator, which is 5 volts at 3 amps. And I would try to feed that right in here. Hopefully these traces can take 3 amps of current. And this would power all my peripheral devices up here. So again, I would have sort of the 2 power supply, and I'd have 2 to 3 amps. So that might be something that I look at in the future if I build some Otto robots that have a lot of servers and a lot of parts. So I hope that's provided maybe a few insights into the problems with powering Otto, and it might help you better choose a power supply to power your robot.